Hey everyone, welcome to CS 109 discussion section. We are in week 3 of the winter quarter of 2021, and this is our second discussion section together. Um, so I thought I would start us off with a brief recap of everything we've been over in terms of how we define probability and how we define random variables, so that we have a really solid foundation moving forward in the course. So let me share my screen. I'm going to share my whiteboard. Can everyone see my whiteboard? No. Okay. Let me retry that again. Second time's a charm. Can everyone see my whiteboard? Some thumbs up? Great. Awesome. Sorry about that, folks. Okay. So let's get the basics. When we're talking about probability, we talk about a set of possible things that can happen, right? So we think of running an experiment, and then when we run an experiment, then we get an outcome, okay? And the outcome is a thing that we say happened. So let's say that the outcome was a dice rolling, right? So I could have a 1, I could have a 2, I could have a 5, right? So these are the outcomes of my experiment, okay? Outcome is a technical word here. Outcome is an element of this set of possible things that can happen. We call this set the sample space, okay? Sample space. And we call an individual thing an outcome, right? Element of sample space is an outcome. Does anybody know what an event is? Can anyone remember? How do we define event? It's also like a technical term in this sense.
Like any set of things that could happen within the sample space. So an event
Yeah.
could be the fact that you roll a 1, or an event could be the fact that you roll a 1 and then a 5.
So we got to be rigorous here. So the first part of your definition was approaching your answer, but the second part was a little bit looser. So meaning I wouldn't endorse it wholeheartedly. It's not that we roll a 1 and then a 5. We're still talking about just one thing happening. I roll a dice and I see a 7, or not a 7. I see 6 or 4 or 3 or whatever. Okay. So an event is a subset of the sample space. That's all it is. Okay. So an event, I'll say um, subset of sample space is an event. Okay. So we got to get our terminology correct. An outcome is a single thing that we observe when we actually run an experiment. An event is a subset of things. Okay. So for example, I could say, what is the probability? We haven't even brought up probability yet. So let me do that actually real quick. So we have this notion of a set. We have this notion of events and outcomes. And when I assess probability, I'm always assessing probability of an event. Okay. I'm always assessing the probability of an event. So I could say, like, what is the probability of like rolling an even number, right? Rolling even. Okay. So this is an event, always. Now, it could be an event that just consists of one element, right? I could say, what is the probability of rolling a 3? And that's it. But I could also say, what is the probability of rolling odd? And that is a coherent notion too, because I define an event to be a subset of the sample space, okay? So now that we've got that understanding, this thing here, this P with parentheses, right? This is like a function, right? Like we normally see, letter in parentheses, and you pass in like a parameter, right? But it's a special kind of function. This is called a probability measure, okay? And what this does is it takes a subset, right? It takes a set basically, and it maps it to the number line between 0 and 1, okay? And the important thing about this is that it has to do this in a very certain kind of a way. And the certain kind of way is that it has to satisfy the axioms of probability, which we won't cover again. But if you remember in the first week, we talked about the axioms of probability. And the axioms were, the uh, uh, additivity axiom, right? Like if I have like a subset, right? Like the probability of this cannot be less than the probability of like just that, right? Like that is implied by the additivity axiom, and other things like this, like probabilities all have to add up to 1, for example, okay? So this thing is a mathematical thing. It maps subsets of the sample space to the number line between 0 and 1, and it has to satisfy these certain axioms. Okay, great. Now we have a pretty coherent picture that of the first several days of class, but where do random variables come in? So I had to give all this to preface the discussion of random variables. So what is a random variable? Does anyone know mathematically what a random variable is? Could anyone tell me?
It's a function from the event space to uh, a number.
Yeah. Close. So it's actually a function from, I'm going to say a random variable. Random variable is a function, right? So that's important, right? That's kind of interesting. It's a function from, and you said the event space,
Sorry,
right? Like
sample space.
from the sample space, yeah. So we're not mapping events, we're actually mapping outcomes, right? And that's why this distinction is important now, okay? So it's a function from sample space, right? Sample space to number line. And when I say number line, I mean any number, any of the reals, right? So random variable x is a function from, I'm going to denote the sample space as omega. Sometimes we've denoted it as s in the past, but I'll use omega for now. And then it's a function from omega to the reals. And so when I say the reals, I mean it's not a probability, right? It's not between 0 and 1. It could be anything. It could be -7. It could be 312. It could be 1.4, right? Anything on that number line. Okay. So I have this sample space, right? I'll draw it again bigger. So I've got, like a 1 die. I've got like a 2 and a 5, right? And what I could do is I could define this random variable, and I could say let x be the value of the die that was rolled, like the upward facing head, right? X is upward facing head of the die. Okay, great. So what this does is it takes as input an element of the sample space and it maps it here. So if this started at 0, well then this this random variable would map that to 1, right? And so on, obviously. Okay. Now that seems, kind of uninteresting. Why did we need this concept of a random variable, right? Couldn't we just make do with what we were doing before in this course where we just had events, right? Like that was fine as it was. We could just say let E be the event that I roll an even number, and then I could work with that, right? There's nothing wrong with that. Anyone know like why did we even introduce this random variable to begin with? This is more of a tricky question. So the reason that we introduced it is because it gives us a really handy way of defining events. Okay, so um, I can say the following. I could say x. Oh, by the way, sometimes I write my random variables like this, like x with this top and bottom thing lines on them, and sometimes I write it just like this. And I interchange between them very frequently, and I don't need to. So as far as we're concerned, they mean the exact same thing whenever I write them. Okay, so I could say x equals 3, right? And x equals 3 is an event. Okay, that is an event. But I could also say x equals 2 or x equals whatever, right? Now this is still not super interesting because we're just dealing with die. But I could make it more interesting. Like I can make another random variable, right? This random variable I'll call y, and I'm mapping from the sample space to the number line. But I am let's say that I map it as 0. I map it 0 if it's odd and 1 if it's even, right? So we'd have different arrows going over there, but it would still be coherent. Okay. So anyways, the reason we use random variables is they give us a handy way of defining events. Okay. And they're much more expressive, right? It's much more expressive to say probability of like x equals 3 or whatever, or x greater than or equal to 3, right? I could do that. That could be an interesting event, right? What is the probability x greater than or equal to 3? Whereas if I wanted to just do regular events, right? Well, then I'd have to like define a bunch more things, right? I'd have to like say like, oh, G is the event that it's 3 or it's 4 or it's 5 or something like that, right? Okay, so regular events are great. Random variables are better, more expressive. The last thing I know this was a longer introduction before we jumped into the problems, but I think it's really necessary. One last thing that I wanted to say was the following. This notation of like probability like x equals 3, this is very confusing, right? Like, what does this mean exactly? If, for example, I showed you this, I said function of x equals 3, right? This doesn't make any sense, right? Like if f is a function and I said f of x equal 3, we'd say like, well, that's just incoherent, right? So why does this make sense? Well, the reason this makes sense is because I said earlier, this is actually an event. And if we want to be more coherent or more more verbose, okay? This is actually shorthand. This is shorthand, okay? So this is actually shorthand for the following. What is the probability of the set of events W or omega, lowercase omega, part of the sample space such that X maps that element to 3? Okay? If you remember, I said this probability measure is a function from events or subsets, right, to the number line. And this is what I have, right? I just built a set with set notation. Okay? So if that was ever unclear, hopefully that is more clear now. You don't have to know this notation for this class at all, but it's really important to get the fundamentals. Any questions about this before I move on? Great. Okay. So, and by the way, you'll never see, almost never, in fact, you'll never see in this course and rarely outside of it either, x described as a function really, right? You know how I wrote it here as a function, x mapping an element of the sample space to a number. But you won't ever see like parameterized almost like this, right? And that's because it's kind of hard to do, right? Like the elements of the set are like a dice, right? How would you draw that, right? How would you draw that? That's basically how you do it, right? And so that equals 3 or 5 or whatever, right? So does that make sense? That's why you're rarely going to see it. Okay. Great. So let's move on now. So I'm going to fly through these. Site Bayes theorem, if you remember, probability of A given B is the probability of B given A is the probability of A divided by probability of B. Okay. And by the way, you can also write this as probability of A, B, A intersection B, or A and B, right? Same thing. You can also write it like this. This is not Bayes theorem technically now, but all I did was I undid the chain rule. If you notice that this is really just an intersection with the chain rule applied, and I just kind of undid it, right? And this is useful in certain cases if you were given a problem in terms of that term, right? Then you would just want to use that form. But most of the time you're dealing with this form because that's what the problem would give you. The next one is, in general, is probability of A, B given C equal to the probability of B given C times the probability of A given BC. What do we think? Thumbs up, thumbs down, thumbs to the side. Don't be afraid to be wrong. Okay, everybody's unsure. So this one is actually, let's apply Bayes theorem. So if we take this term right there, right, we can say, well, let's do this. We can use this form right up there. Probability of A, B, C. Sometimes I use commas between, sometimes I don't. Sometimes I use intersection symbols, sometimes I don't. Don't worry about it, they're all the same thing. A, B, C over C, right? So here I've applied that rule. And then what I can do is I can just say, well, that's equal to probability of A given BC. Whoops, dang it. A given, my Wacom tablets is very glitchy now. Given BC times the probability of B given C times the probability of C divided by the probability of B. All I did was I applied the chain rule repeatedly. Okay, I took this intersection of things and I applied the chain rule a bunch. Then I noticed that C cancels out, and then what I'm left with is that, right? That goes that, it checks. Next question is if A and B are independent, so are A and B complement? Yeah, that turns out to be true. If you look in the slides, Jerry very helpfully put the proof of this in lecture 5, slide 24. So check that out if you have the time. I'm going to move on. If X is a random variable, what is the expected value of X? So this one, a lot of people we're kind of iffy on. I mean, it's just a definition, right? But like, what does it mean? Like, why is it this way, right? So this is just probability of X, right? And sometimes you subscript uh, this probability with the X, right? So by the way, if you remember this, we said capital P, event. This is a probability measure, right? And if you had the lowercase p, sometimes you would just, and you're using a random variable, sometimes you would just use a lowercase p and then subscript it with the random variable you're using, and then just say like 3 or whatever, right? And then this is like, what is the probability x equals 3, right? But I'm saving on notation and I'm not putting the x inside of it. Not a big thing to worry about, but just worth noting. So now that we have this, expected value of x is this, how would you say expected value of g of x? Okay, well, here's one way to do it. We could just say g of x is another random variable, right? Let's say g of x is y, okay? You can do this. If you have a random variable and you apply some function to it, right? Like, I don't know, maybe you added 2 to it, right? It's still a random variable, but now everything's just shifted up by 2. Same thing though. Now we'll call this new thing y, okay? And by the way, sometimes I denote y like that, sometimes I denote it like that. Don't pay attention to the difference. I go back between without realizing. So I could just define this as expected value of y, right? And then that's the summation over, all little y of y times probability y equaling little y. Okay, I could do that. But what this problem is getting at is something more subtle and interesting. You could do it this way, but it turns out for a lot of cases, computing this guy is going to be annoying and difficult. So in order to cope with that, there's this rule called the law of the unconscious statistician. And what this does is it says that if you have expected value of a function of x, expected value of g of x, you can actually write it in this other way. You can actually still iterate over x. And you can just say, this is the summation over x of the function applied to little x times p of x, which is the same thing. You notice that that is the same thing up here, right? If we know this, right? If we like already know that and that's easy to compute, well then this makes our life a lot easier. The fact that we can write it this way, because we can just take every x and apply the function to it, right? But we can also just compute the probability because we already know, because we already have an understanding what px is, right? But the probability of y might have been a lot more complicated. That's why we wouldn't get to it as easily. Okay, and then don't want to keep you too much over time. So this last one is we'll cover is expected value of a summation of x of random variables, right? Overall I. That's just going to equal the. This question is a little bit vague. It just says, what is this, right? It's like, well, what is it in terms of what, right? What is it asking? It's just asking you to apply this rule we learned in class called linearity of expectation, which says this expected value of a sum is really just the sum of the expected values. That is a very important property. You'll see it in the HAT problem on question 2.2, which we'll release the solutions to for, but which I don't have enough time to cover. So that's where I'll end this. Thank you very much. I can stay for a moment or two longer, but I will stop the recording now. Thank you very much for attending, and I'll see you guys next week.
Thank you.
Thanks, Tim. See you.